In this lesson, we're going to be going over combinational logic. Combinational logic are gates connected together to produce a specific output for certain specific combinations of inputs. Now, we actually touched base on this on previous lessons, Boolean algebra, De Morgan's, and so on, where we actually had a set of inputs, A, B, C, D, for example, going into an AND gate, then to an OR gate, creating a final outcome or a final output. Our goal is here to actually do the same thing, but we're going to utilize our universal gates and learn how to convert our various gate circuits to a final NAND gate circuit. Now, what is it meant by universal gates? Well, there are two universal gates. There's NAND gates and NOR gates. NAND gates are actually known as your universal gate. It can produce other gates by utilizing different combinations of NAND gates. If you actually put several different NAND gates in different combinations, you can create different gates, such as OR gates, inverters, AND gates, and so on. Now, there's a couple advantages of doing this. One, NAND gates actually have low power consumption compared to other gates, as well as it's cheaper to purchase a single chip for every use. If I'm able to stockpile one chip for everything, then that actually would save me cost, as well as it could save me space in the long run when actually creating my final equation. And we'll go over examples later of how that's actually done. To provide a visual representation is what is meant by saving cost. If you look at the circuit to your left, we have a circuit that requires two AND gates, one OR gate. Well, if you were building this on a circuit board, it would require two chips and a lot of empty space because one chip is only using one OR gate, whereas the other chip is only using two AND gates. Whereas if you look to the circuit to the right, I'm only using NAND gates and it's one chip, and I'm actually utilized almost all the space except one NAND gate, which could probably be used down the line for another circuit. Here's a representation of how the NAND gate is known as the universal gate. By utilizing the different combinations of NAND gates, we're able to create the other gates as you see on the left. The one you really want to put a pin in and actually become part of your muscle memory is the inverter or not. If you're able to understand and remember that one, doing the method later on to convert any circuit to NAND gates will be easier. Try not to memorize or even get stuck on the other gates of how to create them, because you will not be utilizing those in that method. So we'll go on and practice on later on of how we actually create a circuit to a NAND gate circuit. As stated earlier, the NOR gate was also one of the universal gates. And similar to the NAND gate, if you utilize the combination of NOR gates, you can create just about any gate. So, just like I said earlier, try to memorize how to create a NOT or an inverter using this gate. Don't get hung up on how to create the gates any other way. OR and NAND gates, do not try to create those using this method that you see in front of you. It's going to actually only create more problems and give you more extra gates that you do not need. You're probably wondering why I stressed don't use those tables on the previous slide. Well, I created a circuit here using those equivalencies from the previous slides on the circuit to your bottom left. There are 7 NAND gates. That's 4 excessive gates needed to create the circuit you see on your right. And all I did was just go ahead and use those equivalencies from the previous slides. Well, we're going to use a bubble method to create an ideal circuit which requires the least amount of gates. The bubble method is similar to those methods you see at the very top here. We have a NAND gate, which equals a negative OR gate, and then a NOR gate that equals a negative AND gate. And we'll go over later on in the examples of how to do this bubble method. If you understand how to do this bubble method, you'll actually create a circuit with the least amount of gates, and it'll be an equivalent circuit using a universal gate system. Alright, so let's start off how we actually take a circuit and convert it to NAND gates. Now I want to go ahead and fill in our inputs with A, B, C, D. Pretty typical inputs. And we have 2 AND gates and 1 OR gate. And we want to convert this into NAND gates. Doesn't matter how many, that's just our goal. Always keep in mind, we want to actually create these 2 gates down here. You'll see a NOT OR gate, and then you'll see a NAND gate. If we can create those, then we actually can create a circuit with all NAND gates. Well, this is a fairly simple one. So, by using our bubble method, we can add a bubble right here, and then a bubble at the end here. Anytime you put a NOT or a bubble at the beginning or end of a line or a connection, you have to do on the opposite end as well. It will cancel each other out. So in reality, you're creating 2 NOTs So by doing that, you keep your circuit consistent and you're keeping it the same. So if I remove these 2 knots right now, we get the original circuit we started off with. So I put a bubble at the end and then I put a bubble at the beginning. Well, I'm going to do the same for the other side as well. Put a bubble right here and then put a bubble right there. Well, looking at this, you can actually see that I created already 2 NAND gates and then 1 NOT OR gate by doing this method. And looking down here, a NOT OR equals a NAND gate. So this would actually give us a circuit that looks similar to what you see here. And again, see if my drawing can actually look halfway decent today. And then we draw our inputs. So we're going to have A, B, C, D. Now if we actually took this circuit and actually made an equation out of it, it would look something like this. So let's see if we actually made a correct NAND gate circuit. So A, B, NOT, C, D, NOT, and we're going to one more NAND gate, so that's A, B, NOT, and this is times C, D, NOT, and then we're going to have NOT over the whole circuit. Now in one of our earlier lessons we did De Morgan's, so if I actually did a little chop and swap method, it would actually create A, B, NOT, NOT, plus C, D, NOT, NOT, and of course if you look at 9, or rule 9, 2 knots cancel each other out, so that would actually equal our starting equation. So it looks like we successfully converted a circuit into all NAND gates. And by doing this, this will actually require 2 chips, because it requires 2 AND gates and 1 OR gate, whereas this particular circuit only required one chip, which is a 7400 chip. So if you remember your old digital classes, they actually had to use some of these weird chips and all these digital gates. Well, this one only required just one of these guys. Let's go and do another example problem, that way we can get a little bit more comfortable with using this bubble method. Alright, for this example right here, this one's going to be a little bit more trickier, but we're going to do the same methods we did earlier. So I'm going to do A, B, C. I like to keep a nice alphabetical inputs there. Now, we actually want to convert this all in the NAND gates, same as earlier. So, I want to go ahead and start at this end, just because I'm favoring this end. Go ahead and add a NOT there, and a NOT here. So I just now created one NAND gate. And we also want to create a NAND gate here, so let's see if we can do a bubble there, and then a bubble down here. So that's awesome. Because looking at this, by me having a NOT right here, that actually cancels out that inverter, or that NOT gate. Now, looking at this, that's a NAND gate, that's a NAND gate. However, we have one more gate that is not accounted for. We have an inverter. Well, unfortunately, I don't want to add any dots at the beginning here. However, I do want to get rid of this inverter. And as we talked about in the PowerPoint, a NAND gate that has its inputs shorted together will actually create a NOT, or an inverter, I should say. So A here would equal a NOT here. So another method I can do here is add a single NAND gate. So let's go ahead and redraw this all in our NAND gates, because again, our NOT OR down here is a NAND gate, there's a NAND gate, and shorting the inputs on a NAND gate will create an inverter. So this would look similar to, let's see if I can actually draw somewhat decent today. There's one input, and that we got to count for that NOT, and we're going to short the 2 inputs together. So that's A, there's B, and again, as we looked at earlier, this particular part is one NAND, and this gets completely negated. So we actually have a 3-gate setup here. So we're actually only using one chip right here, one 7400 chip, and we're only using 3 gates. Very little work. Whereas this one used one chip for just one gate, this used a different chip for another gate, and a 3rd chip for just 2 NOTs, or 2 inverters. So this is a little excessive for just a simple little 3-gate system here. So we just used one 7400 chip and 3 NANDs just to make this simple circuit. So now let's go ahead and check our answer just to see if we're correct. So I have A0, B right there, go into an AND gate. I'm not taking into account these bubbles right now, I'm just checking our original equation. So it's A0 times B, and then right down here we have C0, and this is going to an OR, so it's A0 times B or C0. That seems pretty simple. So let's check this one down here and see if it actually has the same output. So we have A going to an inverter, A0, B, and coming out of this NAND gate here gives us A0, B, and then not over both of those. We have C right here. And then we're going to multiply both of these together since we have a NAND gate at the end, and we're going to, of course, invert that. So it's going to be A0, B, not, times, parentheses, C, not over the whole equation. Okay, so we're going to do a little De Morgan here. So it's going to be A, B, not, and then those two, plus C naught. And of course, looking at rule 9, 2 negatives cancel each other out, or 2 knots. So that gives us a final answer of A naught, B, plus C naught. That right there matches our original equation. So we actually successfully created a NAND equivalent circuit. Alright, let's go ahead and do another one. Now this one's going to be very similar to the one we did previously, but I figured practice makes perfect. So, starting inputs, A, B, C, D. We have 2 ANDs, 1 OR, 1 inverter. Alright. Well, like the last problem, I'm going to go ahead and see if we can finish our, or at least start our equation here. That way we have know what our output should look like. So this one's going to be A, B, this one's C naught, and this multiply together again. So it's A, B, C naught. Then we have D. So go into an OR gate. This is pretty simple. A, B, C naught, or D. Alright, final equation. So now, let's see if we can do our method here and actually see if we can come up with a nice clean answer. Well, I want this to turn into a NAND gate. So I'll put bubbles here, which means I got to put a bubble at this end too. And then a bubble right here. So that's already 2 NAND gates knocked out. Well, let's see if I can do that again. Well, I want this to be a NAND gate. The only problem is I got to add a bubble here too. Well, the way we can fix that is actually, as we discussed earlier, we can make that an inverter. So anytime you have an extra bubble, you can always throw another NAND gate in there to compensate for that bubble. That's what I plan on doing down here too. And of course, we have an inverter right here, so instead of adding a bubble here and trying to canceling out, either way we have to add another inverter to compensate for this guy. So, looks like I'm going to have at least 3 NAND gates that are going to be shorted at the input to create inverters. So there's going to be one here, and there's going to be one here. So, I think we compensated for all of our bubbles. And then looks like we have 1, 2, 3, 4, 5, 6 NANDs. Well, let's see how it's going to look on the final piece of work. So I have, I'll tell you what, we'll start at this end this time. We have one here. That's A, B. Comes out to be, again, we got to compensate for that one. So it's going to be another NAND gate. Okay. That comes out. And then we have another NAND gate. The trick is try to keep track of all of them. So we're drawing this one, and that actually goes into one input, and the other input comes from C. But C needs an inverter, so I'm going to go ahead and draw that real quick. And then that will go into there. So right now we took care of that one, took care of that one, took care of that one, and that one. Let's keep going. I see D right here, so let's go ahead and knock that one out too. We'll put that lined up with C. And then, so we got that guy. Last one. Again, this is a not or, and it's equivalent of a NAND gate. So that's another one we're going to use. So that's going to be our last one. So, and then of course connect the last connection. Looks like we got quite a few NAND gates here. So that's accounted for every single one of our circuits here. So you have 1, 2, 3, 4, 5, 6 NAND gates, which is going to take 2 chips, 2 7400 chips, equals 2 7400 chips. Not bad for 6 gates. Whereas this one, 1, 2, 3. This would actually require 3 chips just to utilize 1 gate and then 2 gates and another 1 gate. So you have a lot of extra chips and a lot of real estate that you're wasting in a sense. So of course space is a big deal when creating circuits, as well as cost. By using 2 chips and minimizing space, you're actually creating or saving a lot of money and creating less hassle and less headaches. So let's go ahead and check our answer. So do the same thing we do all the time. AB naught, which is canceled out to AB not naught, C naught, D naught. I try to go with the flow from left to right. That way when I get to the very end, they're all accounted for. Okay, another NAND gate, so it's A, B. I'm just going to cancel it out right now. Okay, and then it's C naught, not over the whole thing. And D naught's right here. So this is going to come out to be an answer of A, B, C naught, not again. I'll tell you what, just to keep it clean, times D naught, and over this whole shooting shebang here. Oof. Yeah, it's going to be fun to use De Morgan on this one. Chop it right there. So we're going to have A, B, C naught, and then 2 more knots, because that one and that one. Sorry to cram this in one little area. Not. Since I chopped it right there, I have to change the signs. It's multiplying, so we're going to have to change the multiplication sign to an OR gate. So an AND to an OR. Well, looking at this and Rule 9, those 2 cancel out, those 2 cancel out. So you're going to have a final answer of A, B, C naught, plus D. And that actually matches our initial answer. So there's another practice problem to get our feet wet. Again, you have to use this bubble method to minimize the amount of NAND gates you're using. If you use those equivalents that we did in the previous slide, if I did it with this one, I'd probably end up double the gates. So let's go ahead and do another problem and see if we can get a little bit more proficient at this type of method. Alrighty, for this last problem, we're going to go ahead and use NOR gates instead of NAND gates. We had plenty of practice with NAND gates. Let's just do the same method. Let's use NOR gates. So same as last time. I like ABC. Seems to keep things consistent. Now let's go ahead and find out what our final equation would look like. That way when we check it later, we don't have to go through all my chicken scratch. So that's A naught, and there's B naught, C naught. We'll do the top one first. So we have A naught times B naught, and down here same thing, B naught, C naught, and then we have an OR. Well, this is pretty simple. AB naught plus B naught C naught. So that would be our final equation, how it would look. So let's do our same method and see if we can actually find the equivalent output of NOR gates. I want to create not AND gates, so I want to actually create bubbles here and here. So if I do that, I'll create a bubble down here too. So that would actually create an OR gate right here, and then an OR gate right here. The great thing about OR gates and NAND gates, anytime you want to create an inverter, you just short the inputs. Let's see if I can draw them similar. So right now, if you use both of these and actually short the inputs, you create an inverter. So these 2 dots cancel out, which is great. This looks like a NOR gate, so that's great. But unfortunately, I put a bubble right there, so I got to put a bubble down here too. Anytime you create a bubble, you gotta put one on the other side. We'll do the same method down here too. Bubble right there. I already have a bubble compensating for that one right there. Again, as long as you put one at the other end, you're good. And then I'm gonna put a bubble right here, and then a bubble right here. So that would actually cancel this inverter out as well. Now we have a OR gate right here, but we want to actually keep that an OR gate and actually just put a bubble right there. So all we'd have to do is put a bubble at the other end as well. Try to, again, what you want to do is you want to make it so you have gates that look similar to what you see below here. That's the whole goal here. So all I did was add a bubble right there. That's a NOR. Then a bubble at the end. And as we talked about, that's how you create an inverter. This is kind of a practice or an art form you have to learn over time. Just practice, practice, practice. So let's go ahead and look at this in a NOR gate. Let's redraw this. So I have A, and it's going into a NOR gate, excuse me. That inverter right there has been canceled out due to that bubble. Two bubbles cancel each other out. And then I have B, and again, I have a bubble right here, so that cancels that B out as well. So that's canceled out, that's canceled out. And C is also canceled out. Man, we're getting rid of all these inverters. So that goes to B. I'll tell you what. B. Did the same thing here. So we have another NOR gate, and that goes to C. So right now we knocked out that one, that one, that one, knocked out that one, and that one. And then we have left is these two. So it's going to go to another NOR gate. For some reason I can never do these curves very well. And then we have one more dot we need to take care of. So what we're going to do is, I'm going to do that inverter. There we go. So right there, it looks like we have a complete circuit using only one chip of NOR gates. So that's not bad. So let's go ahead and check our answer. So A, B, C. Coming out of this, we'll do this one first. A or B, not. B or C, not. Do the same thing again. So right there is A plus B plus B plus C, not, and that's not over the whole thing. And then another inverter. So we're going to keep it simple, just put a not right there. Alright, let's simplify this down just a little bit. Try to move it over here, how about that? A plus B not plus B plus C not. I think we used a Morgan's. Chop both of those down, so it's going to be A naught times B naught plus B naught C naught. So right there, that matches our earlier equation. So right now it looks like we successfully created a NOR gate equivalent circuit.